The modern artificial intelligence industry relies almost exclusively on massive cloud models and external model context protocols to orchestrate complex, multi-tool agent workflows. When developers attempt to pull those identical, token-heavy workflows down to local edge devices, mobile processors immediately hit their physical limits, severely overheating and failing to process the required context. The Biocraft OpenFluke stack is an architecture designed to bypass these hardware bottlenecks entirely, offering a fully offline, vendor-agnostic alternative to deeply integrated operating system assistance. This interface runs a fully autonomous agent equipped with 138 tools, executing commands completely offline, natively across 5 operating systems. The architecture relies on 3 specific pillars: a Go-based inference engine, 1-bit quantization, and a hierarchical router mapping code into the spatial environment. By integrating the inference engine, memory management, and user interface into a single compiled application, Biocraft circumvents the extreme fragmentation that currently stalls open-source edge AI deployment. To understand why this stack exists, we have to look at the primary constraint of edge computing. Standard 1.7 billion parameter models, running on typical 16-bit floating-point architecture, completely saturate the unified memory channels on mobile devices. During continuous inference, this memory bottleneck generates massive heat, triggering severe thermal throttling and draining a device's battery in a matter of minutes. Instead of complex 16-bit matrix multiplications choking the memory bus, the system uses a 1-bit ternary model. This strips away memory-intensive multiplication entirely, calculating outputs using only addition and subtraction. Consequently, ternary execution reduces power draw by up to 82%. Running an active agent requires a continuous loop of speech recognition, language processing, and text-to-speech generation. Without this strict 1-bit hardware-software co-design, sustaining that loop on mobile silicon is physically impossible. Even with optimized 1-bit hardware, a new algorithmic problem emerges: Biocraft's catalog of 138 tools. Injecting all of those stateless JSON tool schemas into a single prompt incurs a massive tools tax, consuming roughly 6,000 tokens of prefill memory. Inside a sub-2 billion parameter model, this overwhelming volume of data breaks the attention mechanism, causing contextual linkages to stretch and snap. This triggers ghost tool invocations, where the model outputs hallucinated fake API calls. The small model simply fails to disambiguate the overwhelming number of options. To satisfy the prompt, it fabricates plausible-sounding code snippets pulled from its training data rather than selecting from the provided schema list. The only way to make a tiny 1.7 billion parameter model execute complex tool workflows is to engineer a strict mathematical reduction of that context window before inference ever begins. Biocraft solves this token bloat using a mechanism called Hierarchical Tool Routing. Looking at the debug log, we observe hop 1. The model parses intent to select a master category, like the contact nest. In hop 2, it dynamically loads only that nest's specific schemas, invoking the contact add function. This flowchart traces the operational logic. By staging the routing process into a category selection followed by a schema invocation, the active prefill context window shrinks from 6,000 tokens down to under 500. We can see this 2-hop execution again here.
The model correctly identifies the user's request to log coffee by routing to the expense nest first, and then executing the exact expense add argument. This staged reduction takes an impossible disambiguation task and scales it down into a highly tractable classification problem for a tiny 1.7 billion parameter model. The industry broadly recognizes this exact context problem. Biocraft's router effectively functions as a highly localized proprietary implementation of the model context protocol's lazy schema loading, executed entirely on device. Getting the model to output the correct text is only the back end of the problem. Passing heavy tensor data across languages from a back-end runtime into a front-end UI framework like Flutter typically introduces severe serialization overhead, crippling the app's responsiveness. This architectural diagram shows Biocraft's solution. The custom neural engine, Velvet, communicates with the Dart-based Flutter UI through a strict foreign function interface bridge. Notice the memory isolation. All heavy tensor manipulation is locked permanently inside the Go layer.
Only the final, lightweight JSON tool call string ever crosses that bridge into the user interface. This ensures the main UI thread never blocks, keeping the application perfectly responsive. When a user sits down at a standard conversational interface and sees a blank chat box, the system's actual capabilities are hidden. The agent acts as a black box, forcing users to guess what tools it actually possesses. Look back at the interface. Biocraft addresses this by abandoning the flat chat box. The 31 backend tool nests are translated directly into interactive 3D citizens and physical locations spread across this planet. By giving tools a physical location, the system leverages human spatial memory. It provides the user with an embodied cognitive map that visually communicates the precise boundaries of the agent's offline capabilities. This aggressive edge architecture does come with objective limitations. A sub-2 billion parameter model, especially one heavily quantized, struggles with raw intent classification accuracy. This scoreboard tracks the system's live evaluation tests, showing an exact 54% overall end-to-end task success rate out of 563 completed runs. The specific failure mode lies in multi-intent tasks. The 1.7 billion parameter model frequently misclassifies complex strings that require jumping between multiple nests. Because the architecture is deterministic and designed to fail closed, a single routing error halts the entire loop safely, preventing destructive operating system commands. However, when restricted to single-intent tasks, the accuracy rises to a much more viable 74%. To resolve this accuracy bottleneck, the stack relies on an architectural strategy called device tier model laddering. The underlying 1-bit architecture scales cleanly. As host hardware improves, users can seamlessly swap the tiny 1.7 billion parameter runtime for 4 billion, 8 billion, or 27 billion parameter ternary models. A 27 billion parameter ternary model can execute efficiently in just 3.9 gigabytes of RAM. This provides the exact contextual depth needed to solve complex, multi-intent routing failures, fitting on a high-end smartphone without requiring a single change to the core software structure. The Biocraft stack proves that by meticulously controlling the memory boundary, leveraging ternary inference, and staging context hierarchically, a powerful, vendor-agnostic spatial agent can operate entirely offline today.